Okay, so this this the final question. By the way, I did upload the Excel documents, so they're up there. And the final question doesn't have anything to do with water usage. It is has to do with this other column in the data right here, the opinion on legislation to mandate energy efficient water. So the way that you fill out this column is you just write the number that said yes and the number that said no. It's still the sample size is still 7, but now you got 2 yeses and 4 no's. So you could even resort if you want to go quickly. In Excel, you can highlight all the columns. You can go to custom sort, and then you could say, I want to sort on dwelling type still, but then I want to, let's see, add level. And then sort on, then by opinion on legislation to mandate energy. So you can hit OK. And if you do that, you'll get them aligned so that you can more quickly see what they are. So here you've got 5 and 2, and then here you've got something and something else, and so on. So you fill out the table that way, and then you plug it into the large formula. Remember that P is the proportion, and so you want to find out the proportion of residents in favor of the proposed legislation. So that's the number that responded yes, divided by the total number of yes and no's. I mean, you could figure out, you get pretty much the same answer since it's just 2, yes or no. You get pretty much the same answer if you just did no, but if there were more than 2 answers, then you wouldn't. But yeah, you're just going to fill that out. So if this is 2 and that's 5, then the proportion is 2 divided by 7. Okay, then you're going to get a different proportion for townhouses and for residential. So if you look at the formula, the formula is big N is still this 100, little n is still 7, and then the x in this case is 2, but it'll be different in each one. So all you're doing is you're summing up every proportion multiplied by its population size, and then you're dividing by the total of that proportion. So, each of these is just, it's kind of, I think I said this last week, it's kind of like doing a weighted mean. You're doing a weighted proportion here. Okay? Yep. And then you need to do the next one. And if you have trouble with it, we can talk about it more next week. Here, I left this empty, but you probably should be able to do this now, because this is the standard error. You multiply it by 1.65, 1.64, or you can use this, which will give you the same number. Okay. All right, so let's at least talk about the next chapter real quick, because you'll see that there's some concepts that are introduced in terms of hypothesis testing, but there's only one new concept that's taught in terms of the I know I already downloaded. There's only one new concept that's taught in terms of a statistical test, and we can put that off till next week if we have to. So here we are. But this way you can at least get started on it. I thought I downloaded this already. Probably did. So yeah, we have about 20 minutes, but only 25 slides. So might not get through all of them, but today we're going to talk about classical hypothesis testing. That's the major point. This other stuff that we're going to talk about, where we're talking about using p-values, we've really introduced this concept. When we talk about confidence intervals, another way to think about it is if the sample mean is going to be near the population mean, 95% of the time it's going to fall within that confidence interval. Another way to express that is we could say that if we want to go ahead and make a decision, that's what hypothesis testing is all about. I want to make a decision based on the data. And so if I want to make a decision, I could use a statistical technique, and understanding what the confidence interval range is going to help me to make a decision that I'm comfortable with. Okay, that's what we're doing. And so when we say p-value hypothesis testing, we're saying, okay, well, I either want to say yes, it's this way, or no, it's not that way. And what's the probability that I'm wrong? That's what we're getting into here. And to actually apply this, just for this week, we're going to do a really simple example of this, but it's a commonly used example of this, and that is to look at what if we sampled a population and we wanted to compare that sample, we want to compare the means of that sample, two different types of that data, or two different proportions of that data, and come up with a result. And this is built into Excel, so we don't need to do it all by hand. Okay, so and by the way, when I talked about giving up on Python, there will be some examples later, but we won't be calculating like fundamental things in Python. So when it comes up later, when we start talking about other statistical methods, but they'll be pretty simple calculations. Basically, we're not doing the calculations at that point. We're just saying, here's the data, and we want to be able to interpret the results. Okay. So a hypothesis is simply a claim about a population. And so we want to be able to make a claim about a population. That's where we're going. That's what I explained earlier on the slide. Okay? So specifically, we want to make a claim about an unknown parameter. In other words, some measure of that population. It could be the mean, which it is most often. It could be the total. Why would we want to do this? Well, we might want to do this in order to refine models that we've developed. If our model predicts the mean, we might want to find out if it's working, because it might be different than what we expect, but if it's not different enough, is it really significantly different than what we'd expect in the population? So we can use that to develop laws and theories, and we can, I already said the example of, we can use it to help, like, say things like the Earth is getting warmer with global warming, or I changed this one thing and the sample means changed this much in my model. So how much did it really change, or is it really changing, or is it just the random chance that happened? Okay. All right, we already talked about how proper sampling is essential. So remember, that's the case. You gotta have proper sampling in order to do this. And that is one reason why you're doing that. You do that 3 different systematic samples, and you're gonna see which systematic sample type got closest to the original proportions. And anyway, that's kind of a side note. I'll talk about that some other time. Okay, so here are the classical steps to doing a hypothesis test. So the first thing is to come up with a null hypothesis. And doing that involves identifying what that unknown parameter is and making a statement about it. And usually it implies that there's no association between an explanatory and response variable. In other words, we're saying that what we're saying is that oftentimes the null hypothesis is going back to the is the Earth getting warmer theory. The null hypothesis implies that even though something has happened differently to both, we could say, the past record and the future record, even though something different happened, that's still the same pattern. So there's no association. We might have more hurricanes. We might think we see more hurricanes. But what we're saying is our null hypothesis is that there's no difference, that the number of hurricanes is not increasing. In other words, we're saying that there's not anything occurring. Or, I don't know, I'm having trouble thinking of another example right now, but usually the null hypothesis is that they're the same, that the things that we're testing are not different, that there's not something changing them or causing them to happen. The alternative hypothesis is the opposite, that they are different, they are changing. So it's contradictory to the null hypothesis. And so the next thing that we need to do is select a test statistic. And the test statistic is the quantity that we're going to test, the quantity that we're going to derive from our sample data and test between the null and the alternative hypothesis, like the mean, or lots of times it's the mean. It could be the total. Then we need to select a rejection criteria. This is where we get into how confident do we want to be that we're making the right decision. Because if we reject the null hypothesis, in other words, if we say the null hypothesis is wrong and we accept the alternative hypothesis, we could be making a mistake. Or if we do the other thing, if we accept the null hypothesis and reject the alternative hypothesis, we could also be making a mistake. Either way, we could be making a mistake, no matter what we do. But if we understand the statistical principles behind what we're doing, we can be confident, and we know how confident we are that the answer is correct. Okay, so this is where it's basically just an extension of last week. This part is the confidence interval part. Then we need to calculate this test statistic, which is often done in software, but that test statistic is the statistic that will compare the values that we're looking at, and then finally make a decision regarding the hypothesis. So we accept or reject it. All right, so here's some example of a hypothesis, or not really an example. This is the null hypothesis, and the opposite, the alternative hypothesis, is that it's some other value. Okay. We could even test whether or not the true mean is just any arbitrary value. We don't really have to have any reason why we might know the population value, but we could be comparing one sample to a population, or comparing two samples to each other, or comparing 10 samples to each other, or 100 samples to each other, or a distribution, like the Poisson distribution. One of the things we're going to talk about is, remember when we came up with a population proportion, and then, an observed proportion, and then the Poisson probability proportions, and we compared them, but we just compared them quantitatively. Well, what if we want to say, if this really is random, then they should be similar, but how similar do they need to be? Because random doesn't mean the same answer always occurs. It just means on average I'm going to get the same answer. So there's lots of different hypotheses to test out there. All right. One way to state these, particularly for what we're going to do this week, is to state it very simply. Here's a typical claim that the mean is equal to some value, the hypothesized mean. So the claim of equality is what's called the null hypothesis. So in other words, I could say that my null hypothesis is that the average age of everybody in here is 23. Okay? I know that it's probably not. Actually, I don't know. Maybe I'm way under. So the average age of everybody in here is 30. Right. Yeah, it's not an undergraduate class. I mean, I know there's some undergraduates in the course, but anyway. I was just making up a number. But that 23 and saying it's equal to that is the null hypothesis. The alternative hypothesis, by definition, is that it's not 23. And this is where we get into that one-sided and two-sided test. So if we say that it's the alternative hypothesis, if we say it's not 23 or it's not equal to some mean, that's just a two-sided test. In other words, we're building a confidence interval about 23 and seeing if our value fits into that confidence interval. And if it fits into that confidence interval, we're good. Well, it's a one-sided test if we say, I believe that I believe that it's equal to 23. Well, if I rephrase the question and say, the average age of the people in this class is greater than 23, then that's the second one there. And it's a one-sided test. In other words, we're not concerned with building a confidence interval about the mean. We know that we just want to be right 95% of the time that we're within the one side of it. Because we already know that, or we're only testing whether we're in the one side of it. And so what that allows us to do is basically change the width of that confidence interval, because we're not concerned with that other side. We know that we're comfortable with it never happening. And so we just can use the error under the one side of the curve. So anytime you ask a question greater than or less than, it's a one-sided test. If you're saying it's not that, it's a two-sided test. All right. So remember I said that no matter what we choose, there's a possibility of an error, right? If we choose to say they are equal and they aren't equal, then we've made what we're going to call a type 1 error. It's probably described a little bit better in your book, but that means that if they really are equal and we said that they aren't, maybe I didn't say that right, but yeah, if they really are equal and we said that we aren't, we made an error, and that's called a type 1 error. Okay. If they really aren't equal and we said that they are, we've made a type 2 error. So there's two types of error we can make, and there's two correct decisions we can make. So we want to maximize the probability that we're making a correct decision. Okay? And those two terms, we refer to them as alpha and beta. Okay? The probability that we make the correct decision is 1 minus alpha. So that alpha is remember when we do confidence intervals, it's the small, like if we say we want to be 95% confident, then that means that we're going to be right 95% of the time. So another way to say that is that we're going to be wrong 5% of the time. So that's why this is 95. In other words, if we choose we choose, hey, I only want to be wrong 5% of the time, then we know we're going to be right 95% of the time. This actually should be over there. I messed up. Let's see if we can. Yeah, I don't know why that. Maybe it's because I didn't do that. Okay, there we go. So the probability that we're wrong is just out. So this is that we made a mistake. I'm sorry. This is that we made the correct decision. It's 1 minus alpha. So in that case, 95% confidence interval. 95, 5%. Now these are a little bit harder to define. These type 2 errors that that are talked about in the book. But the theoretical way to describe those is that that term beta, okay, and by the way, in the book, it's this is like flipped on its axis. The table 9.2 is flipped on its axis. State of the world is labeled as null, hypothesis, and reality. Okay, so we could control this really easily, but this we have to think about a bit in terms of how we get that value. All right. Oh, that's way too small. Okay. Well, I'm thinking this is probably a good place to stop. But if you want to try to attempt the homework, really, what we're going to do now, instead of doing the confidence interval, the focus of this one is, instead of finding the confidence interval, you're working back and you're finding the z value, and then finding the area under the curve and deciding if that area under the curve is bigger than the mistake that you want to make. So in other words, if you work backward, you're doing the same thing. Confidence interval is you're finding the width of that size. Now we know where we are, so we rescale it back to the standard normal distribution, find out what the z value is, then find out the area that's under the curve, and yeah. Another way to say that is we find out where we are. Here, I'll do this right here. We find out where we are. Maybe we're right there. And if we're right there, and we know that we should, that it's unlikely that we're wrong if we're anywhere in this area, then it's okay to reject the null hypothesis. Because if we're wrong, we're only wrong like 5% of the time, or this case 2.5% of the time. Okay. All right. So let's leave this one to finish up until next week. But the reason that one of the reasons that I was struggling at the beginning using those T statistics is because here we're actually returning the statistic that we want, yeah, the numeric value at which to evaluate the distribution. So we're getting the area under the curve. So this is one of the tools. You can also use, there's also the normal dot dist, not normal dot inverse. So if you need to use the z table, you would use normal dot, not inverse, normal dot dist, and you give it the x value, and it returns that area for you. That you need to do. All right. Okay. So we'll do an example at the beginning of next week's class. I'll bring up the homework. So. you can at least get started on it and finish off exercise 8 now. And if you have any questions, let me know. So it's 3:40 though, so some of you need to go. Anybody have any questions?
Chapter 6.
Okay.
Which I don't know if you guys misheard, but do you want us to use these maps, or is there data from ArcGIS that we can use?
That one doesn't have any.
That one doesn't have any, because I was looking for.
Oh wait, no, there is.
There is? Where is that?
For that one, it's in the project data. So if I bring that up, it's in. Basically, I think the easiest way to get to it is to open up that QMSA. Maybe it's QMSA week. Let me see what it is.
I figured that would be a whole lot easier to do chapter 6 than doing the
Yeah.
I discovered it was in there after.
Yeah, I remember. I did make it.
I'll wait out.
I actually just Googled. I mean, anybody could do this. I just Googled airport locations, and I got it. But it's chapter 6. Yeah, I did put that data in there too. Yeah, that's chapter 6. Close that back up. 5, 6. Yeah, airports is right here. So I'm going to call this new map. Rename chapter 6. Throw on airports. And when I downloaded it, it was all the airports for the whole world. I did pull out just the United States airports, but even that's too many. So
You just need the ones that are, I guess, listed on these maps, because they don't even count.
right. So how would you do that? Yep, you could do a join, and this field right here is in there, is in that table, the ident field. So, if you might have to do that other trick we talked about before. So here I've got my data. It's workbook data, right? It's in that workbook data set. I mean, you could actually even do that calculation in Excel, but I mean in ArcGIS. So it's this airport data one. Okay, so here's my airport data. It might not join straight up, but it might. But if you have a problem, you can always export the airport data. Let's see though. We take airports and we do a join. Let's see if it works. To add join. It's thinking. Okay. Yeah. It's called ident, and in here it's called airport code. Is that right? So airport code. And then if you uncheck keep all target features, it'll discard the ones that aren't joined. And, and it does look like it worked. And so yeah, you got to calculate those extra values. You could do it right in ArcGIS, or you could do it in Excel before you do that join, and then they show up.
In 1 and 2, it's asking what is the probability for each city having less than or having. Are you looking for like a particular number, or can we just go on because I know that the lower standard deviations indicate that the values are closer to the mean of the set, and that the higher ones measurements indicate that they're spread out over a wider range. So because they give us a standard deviation in chapter 6, can we just, I guess, make general statements about that, or are you looking for certain probability numbers to express that?
Yeah, so you're saying, can you just give a qualitative, like it probably isn't or it probably is?
Yeah, because I mean, I just based it off their standard deviation. And if, Syracuse, they said, was 131.7 average snowfall, well, that would indicate, based upon their standard deviation, that, yeah, they're likely to have more than 100 inches.
Right, but yeah, you should. So what's the exact question? I can pull it up if you want.
Number one, it says, what is the probability of each city having over 100 inches of snowfall in any given year? And then they provide us with a table of Buffalo, Syracuse, Central Park, with the average snowfall and the standard deviation. So there isn't a table within the workbook data that showcases this, but I assume that we just made a qualitative assumption.
Yeah, let me pull it up. Because where is, there it is. Modules 6. Okay. This is the question you referred to? Okay. So, yeah. So it's asking you to use the normal distribution. Consider the yearly snowfall for Buffalo. Yeah. What's the probability of each city having over 100 inches of snowfall? So you're basically going to use the normal distribution, and you definitely could just use the standard deviation if you're confident that it's correct, because you're just answering a yes or no question, right? Well,
you could, but then 3 says, what's the probability of each city having between 80 to 100?
Yeah.
And so I didn't know if there was like some sort of competition
Yes.
you wanted to showcase in these questions.
Right. So each of them does definitely have a mathematical way to do it. So what you do is you're It's going to try that. There we go. Okay. So what you're doing, this will be a little bit easier. Okay. Okay. So here's the standard normal distribution. And the standard normal distribution, this is 0, and this is 1, right? Mm-hmm. But you're being given the values 99.6 instead of 0. Mm-hmm. All right? And instead of 1, we have 31.28. And so what we want to know is what's the probability that it's 100, right?
Mm-hmm. For the first one.
Yeah, so 100 is right there. 100 or what?
And then the other one is 50 inches.
No, but 100 is...
Over 100 in any given year.
Okay, so the probability is over 100 or more. So if 100 is right there, what that question is asking you is, what is the area under the curve right here? That's what it's asking you. And so, how do you solve that problem? Well, the formula... How does it know that I picked up green?
Smart.
It's smart more. Okay, So the formula for getting the z-score out of the values is right is that, I mean, it's all over the place. It's the x, the mean that you're or the value that you're testing minus the mean divided by the standard deviation will give you the z-score. I mean, it's the first time it's presented is 6-1. So here we have. So here okay. So the z is equal to. This is just the z-score, but it was getting close. Z is equal to x minus x bar. That's the sample mean divided by s. And all that does is it's like, I mean, this is really the formula for like shifting something and scaling it, because this term is the bias term basically, and then the scale term is standard deviation is the scaling term. It's like growing it or shrinking it. So we put 100 minus 99.6, and we get, and what's S? Does it say what S is? Oh, 31.228. Yeah. So this is equal to 0.4 divided by 31.28. And what's that number?
This is as far as I got on this one. Because is there like a z-score chart?
There is.
Where's it?
It's in the back of the book.
Oh my god. Okay. That helps.
That would be point
You could also do it in Excel. What's that?
0.013.
Point zero.
It goes 0.01278772.
How are they doing that? 1.0127. Okay. That like shifted everything all of a sudden. Like I didn't write there.
I think it's so you don't write over the image that you already created. It's trying to, it thinks it's doing something good for you.
Really
Too
well.
smart.
Okay.
Too sentient.
That 0.127 is telling us how far away it is from the mean. Is that going to make sense? Because 100 is really, really close to the mean. So that's telling us if this was 0, if that value 99.6 was 0, this is how far it's away on the standard distribution. So that value 1.027 is the distance away from the mean, assuming the mean is 0. So what we want to do is find out what that green area is. So using the book, then if it's page 303. We want this green area, but what it's actually giving, the book's giving us this area. That's what that means, that A thing means. And we're at 0.127. So 0.1
0.0127.
or 0.01. We only have 2 decimal places on this particular Z table. So we have 0.01 or 0.02. We can choose between those two. So 0.01 is closer. So the way that we read this is that the area under that curve is 0.0040. In other words, that little red sliver is 0.0040. You see that, Addison, on page 303?
Wait, where? Okay. So which one? Am I looking at the top numbers up here or this? Yeah. Okay. So we're in between here, right?
Yeah, we're in between these two, but we're much closer to this one.
Okay.
Because if we're going to round it to these numbers, we'd be there. Yeah. 0040. You got your book? So that number is 0.127. The closest number we have is that number. And so 0.01, that's the way we get that. So that's that number.
0040.
Yes. So 0040, I guess I'll write this over here so that it won't mess up. 0040, and we want to get the green, we're going to take 0.5 and subtract it from 0040, which will be, that'll equal 0.4996, right? Like if I took 0.5 and subtracted that?
496.
Just 19?
Yeah, where did 0.5 come from, though?
Okay, that's a good question. 0.5 is the area of the green and the red combined. Because on the standard normal distribution, the area under this curve is 1. And so half of it is 0.5. So it's giving us, it's always giving, this table is always giving you the red. And the green is what you want in this case. Because it said, the reason why you know that is because it said 100 or more. So what's the probability that we're going to get anywhere along this part of the number line? That's what it's asking. So in the next one, all we need to do is change the numbers. So we change, like this changes to 131 point whatever, so that changes, this changes to 131 point whatever, and so on. So the probability that we're going to get, this is the probability, by the way. That's the answer.
Now, if I used Excel and got 4949, that's the reason.
4949, yes, because this is really 1.227.
It's like extended. That was just the abbreviated. So if we would have done the whole thing.
Well, that's all that I was just going to show that, by the way.
How do you do it in Excel?
So in Excel, there is, I want to do it in class data. I guess I don't have that up anymore. I'll just do it here. So you just say, equals norm.
We can't see it.
Oh. Hold up here. Okay, so the way that you do this is you say equals norm this, and you're giving it an x value. The x value is the thing that's like,
96. Or no, 100.
that's the mean. That's the 100 in this case.
100.
Yeah.
So 100, and then the mean would be 99.6. The standard deviation, 31.28. The cumulative would be.
In this case, you do want cumulative because it's the area under the curve is what you want. If you say false, it's only going to tell you the height of the curve at that point. Okay. I mean, sorry, true. I just said that. Okay, now, why isn't that number right? What do we still have to do there? It sounds like Dan, you know what we have to do there.
Subtracted by.
Right, because now we've got the area to the left.
Right, yeah.
And so we want the area to the right. And so we can either put that into the formula. So it'd be 1 minus. So now it's 0.495.
How did you put that to the
What did you say it was? You said it was different.
Or you said 4949.
4949.
That must have been some problem, but I can't find where I did it.
Yeah.
You just put 1 minus right in front of it, right?
Right, I put 1 minus because I'm trying to get the area to the right. It's greater than 100.
Can you pull up the function more
Yes.
so I could write that down?
1 minus. Okay.
So you just put it right in front of it.
Okay.
Mm-hmm. And then you know,
So much easier to do in Excel.
yeah, well, you don't have to look up the table. I mean,
I like learning it by hand though. It does, it kind of helps explain it a little more than what I try to understand in Excel. I'm not computer driven.
yeah, well, I mean, it still helps to draw it out, even if you do it in Excel, because that, you don't necessarily figure out where everything goes until you do that. I mean, 199.6, where does it go? So the second one though is, you know, now you could just do this as a, table, right? So you could type in all the numbers. So 100, 90 what? 99.6? What's the second number? Oh, I got it. Yeah. 131.7 and, oh wait,
It would be 99.6.
it's always 100. And then I need 31.28. 44.96. And then 33.39. Wow, that's way less snowfall. 19.04. Okay. And then this is always 100. So this is equal to normal dist. That's the x that we're always concerned about. Mean, standard deviation, true. And then we actually want 1 minus in each case. So I must have messed up the first time, right?
I don't know. I like those.
So that's the number you had?
Yeah. Still can't figure out where I did it.
You know, I might have, because I manually typed in 99.6. I might have typed it in wrong. I might have done that wrong. But yeah, those are numbers. So what's the probability that in an area that, on average, sees 33 inches of snowfall with a standard deviation of 19? What's the probability that they get a year with 100 inches of snowfall? It's like nothing, right? And that makes sense. All those numbers kind of make sense. Here, this one's probably, I mean, this one makes sense because it's right there on 100. But this one with 131, what's the probability that it's over 100? It's that way, like 75% of the time. Most of the time, 70. In other words, you know, on average, three out of every 4 years is over 100.
So you could technically base this just off the standard deviations, but you do want us to calculate it.
Yeah, for sure. And then the next question, what's the next question?
It's just for 50 inches. And then, so we would just repeat this, or less than 50.
Less than 50. So yeah, you put 50 here, but you'd reverse this so you didn't say 1 minus. Right, because now you're, you know, if we go back to that other screen, now you're trying to get like this area right there. But you're still given this red area.
Yes.
Like if you look up on the table, you're given the red area. So to get this, I mean, you get this red area, but to get it over here, to get that, you have to flip it around. That's why you don't say 1 minus, because now the number that Excel is always giving you is always the.
It has a slide bar down there to where you can just keep going to the right and create one continuous document.
Yeah. So
It's just a
can you like send this to somebody?
Yes. So you see that QR code?
Yeah.
You can scan it, and save it, and send it out as a PDF.
Oh, there you go.
What?
You know,
We have one of these at the youth center that I want. I had to be the only one to learn how to operate.
Yeah. So it takes that. It's always to the left of it. is what.
That explains it so much more.
Now,
Yeah.
what was between what and what?
80 and 100.
80 and 100. So in that case, if you're going to do it the Excel way, you get the value for 80, and it's all this area. Or sorry, 80 would be somewhere here, and 100. And you basically just take the difference of the two.
Oh,
Because
okay.
you get two.
Wait, so you have to get, okay, so you're doing in between two?
So here, I'm just going to copy all this stuff down here, right?
So just the differences of the sums.
Oh, it's between 80 and 100. Yeah. So this is 80, 80, 80. But I don't want to do the negatives. So this is the probability that's less than 100 if I take out all these negatives. Right? Does that make sense or no?
Are you on Excel?
I'm in Excel. This is the probability that. So 1 minus means the probability is greater. And without the 1 minus, it's probability is less. Oh,
Sorry.
you're right. That's what you were telling me.
For a second, I thought you were about to do something on the smartboard.
So here, this is the probability that it's less than 80 because I took out the 1 minus. This is the probability it's less than 100 because I took out the 1 minus. So does it make sense that these are always greater than those?
Yes.
Because we're more of the distribution. And so what we're saying there, so in order to get the right answer, you just take this and subtract that. And that's the probability that it's inside that range.
Okay.
Right.
That.
This is very helpful just to have some confirmation that
You're the only one that knows what you're doing.
Something else in the crowd.
Right.
Poor Dr. Akers had to come hang out with us a lot.
I think the mellow yell's wearing off. Oh, I gotta sit down.
All right. I feel,
Thanks for that.
Yeah,
That
thank
was
you.
helpful.
I've been hung up a little bit on
Because
six.
we were both hung up on 6.
Yeah, if you have any questions, yesterday I met with a couple students.
You know, I already told you yesterday.
What's that?
I said, you know.